All right, multiplying polynomials and special products. There's really one very big special product that you need to pay attention to, and hopefully you'll see exactly why. But let's use the very general type to look at this. Okay. And what we're going to do is we're going to take two binomials. Let's say it's u plus v, and we'll multiply it by u minus v. And we want to know what this equals. So what we can do is we can use that same principle of multiplying polynomials and perform this out. So this would be u plus v times the quantity u minus v. And then what we can do is, again, we can just circle them. So I'll just circle them in a different color. And then we'll multiply them out. So I'll use this, I'll just use one color this time, but it'll be u squared. That would be a positive, right? Because they're both positive. So that would be uv. And then we have, one's positive, one's negative. So when we multiply those, we're going to get a negative. So that would be negative uv. And then the last one would be negative v squared, right? Because we have a negative v times the positive v. And then we just add them together. So we get u squared. And then notice what happens to the internals all the time. They just cancel. So we're left with this. And this is a special guy. This is called the difference of two squares. So if we can do this out and look at the cheap shortcut, we have let me just put this here. We have some binomial where you're adding two things, and you're having the same binomial where you have a difference of things, and the end result is always going to be u squared minus v squared. So you'll always square the first and square the last and take the difference of them. Now, we can do a quick example of this, so let's do that. And let's just say that what we have here is 2x plus 3 times the quantity 2x minus 3. Well, if we do it all out the classic way, we can prove this, but all we have to do is realize that we're going to square the first, so that would be 2x squared, and then we square the second. Well, either way you look at it, it's a 3, so if it's positive or negative 3, we can just square that. And then the sign is always going to be a difference. So this looks like it's going to be 4x squared minus 9. And let's just check that as our classic multiplication. This would be 2x plus 3 times the quantity 2x minus 3, which would give us 4x squared plus 6x minus 6x minus 9, and it looks like we have the same darn thing. So there is one more case that I'd like to talk about real quick for the tutorial, and that is something very secret, but we're not going to talk what the secret part of it is. And it's called the binomial theorem, but let's just play a game for a second. We're going to make a triangle, and I'm going to leave a block out here, and we're going to do a triangle. And what we're going to do is I'm going to make some diagonals here of ones, and I'm going to make them increasingly outward. And what we're going to do is just play a game, and we're going to see what we can build. So if we add these internal beasts together, we get 1 and 1 or 2. So let's make another row here, and I'll go out one more, and we'll make these ones out here. And then we'll play the same game, that if we do these internals and add those together, we're going to get 3. And if we add these and... Why is that not red? I thought I picked red. Did I pick red? I thought I picked red. Okay, so that would be 2 and 1, or another 3. And let's draw this out just one more time. And we'll go out 1 here, out 1 here, and let's do this in pink. So 1 and 3 make 4. And we'll do this one in red since one of them's already red. And 3 plus 3 is 6. And let's use dark purple here. We have 3 and 1 make 4. Now, this is an interesting pattern that we're building, and this is called Pascal's triangle. Okay? And what this does is it represents, well, let's see. Well, I'll tell you. So this first row represents the sum of 2 things raised to the 0 power. Now, how do those represent each other? Well, what is a plus b to the 0 power? Well, it's equal to 1. So let's take this next row. This would be equal to the sum of 2 things raised to the 1st power. Well, what do you get when you raise that to the 1st power? Well, it's just that same thing back, or a plus b. And now, what would this one become? Well, this is another interesting case. This is the sum of 2 things all raised to the 2nd power. And what it looks like, I'm going to need to make a little more room here, so I'm just going to move this over just a bit. And what this is a squared. Oh, you know what? Let's not do this one just yet. Okay? We'll do that one in a second. So this one represents the sum of 2 things all cubed, and this one obviously represents the sum of 2 things to the 4th power. So, this is a very quick way where you can multiply binomials to any power that you wish, as long as you understand the pattern. Now, later on, we actually do go through the binomial theorem, but for right now, understand how we're looking at this pattern and the ratios, because the next problem I'm going to do will allow us to maybe simplify this just a little bit more. So, let's just take a very, very easy example first. So, example 1, the easy example. Let's just take x plus 1 all to the 2nd power. So if we did this problem out, what we'd see in the classic version, we would see that we have x plus 1 times the quantity x plus 1, which would give us x squared plus x plus 1. You add them all up, you get x squared plus 2x plus 1. So, what's the idea? You square the first term. You see what I'm trying to hint at? This is not mathematically correct, but if you think about it, your square, it is mathematically correct, but I don't want you to think it's distribution. Okay, it's not distribution. So it's x squared, so let me put that in purple here. In fact, let's just erase it and put it all in purple. So that would be square the first guy, square this last guy, so that would be plus 1 squared, and then take 2 times the internal product, x times 1, because we're just multiplying those two. And that's what this is saying right here when we do the actual problem out. So now that we've actually done the products and shown that they are in fact the same darn thing, let's look at what it means to generally look at a plus b squared. It simply means take the first term and square it, take the last term and square it, and then take 2 times the internal product. And I'm hoping that you see that all of these are the same darn thing. So let's just try one more example here. And let's try a little more complicated one. How about we take 2x minus 3 all squared? And now we're going to do the same thing. We're going to just square the first. So let's write it down. We square the whole first beast. We're going to square the whole last beast. And then we're going to take 2 times the internal product. So the internal product is going to be 2x and the negative 3. So once we've done all the multiplication out, we can see that this is just going to be 4x squared minus, well, 2 times 2, 4 times 3, or 6 times 2 is 12x. And then notice that the last term, you're always going to have the addition, which is nice. So that just 3 times 3 is 9. Now, again, we encourage you to check it by just doing the product out manually real quick, just to see that this is 4x squared minus 6x minus 6x plus 9. And when you do that all out, we do, in fact, get the same darn thing. So our cheat, if you will, is a very good cheat. Now, let's just take a slightly more difficult problem, but not really. Let's just pick x plus 1 cubed. And what we know from Pascal's triangle is that it has a ratio of 1, 3, 3, 1. So here's a trick to show you. Well, let's not do that trick just yet. So let's actually let's do the trick. So what do we know? We know that we're going to have cubes everywhere that we look. So what this ratio is saying is let's do it as this. Let's call it what they are. These are coefficients. Okay? And they're coefficients to terms. And what this represents is the cube. So I'll just write cube here. This is an internal product, 1. This is an internal product, 2. And this is a cube as well. So this is cube the first, cube the last, and now we're going to do 2 times of internal products. So the way that this breaks down first, and I'm going to do this with the exact problem, and hopefully you'll see the pattern that I'm going to draw out in a second. So what we have here is, well, let me just, we'll do it. So what this would be is x cubed, so I'm cubing that first, and I'm cubing the last. And notice that the signs are they could have a possibility of changing, but because it's positive, it's not going to change here, which is nice. And then we have to take 3 times an internal product. So the internal product is actually going to surprise you for a second. It's going to be 3x squared times 1. And then the next one is going to be plus 3 times x times 1 squared. And now you'll notice we have our expansion. What we call this is the expansion. So if we just pull this together, we have 3x squared plus 3x plus 1. And you can double check that to see, but if you see the ratios, there's really a 1 here, a 3, and there's really a 1 in front of that 1. Now, hopefully you see a pattern here, and you might be only see it as part of it, but what I want you to keep in mind here is look at the exponents. So here is the general rule for a plus b to the third power. What we can see here is that it's going to be a cubed plus 3a squared times b plus 3ab squared plus b cubed. So if you notice, the lead coefficients, so here, let me highlight it, a cubed, we can see the exponents are counting down on a's. There's actually an a to the 0 right here. And it's a little hard to see, but I'm hoping that you see that the lead coefficients exponents count down. But what happens to the secondary variable here, b? Well, you'll notice that they're actually counting up, because this is really times b to the 0, and then we have b to the first power, and then we have b to the second power, and then we have b to the third power. So this gives us a very powerful way to expand binomials. So if we just looked at the fourth for a second, and this is running a bit long, but if we just look at the a plus b to the fourth, then this would be, well, a to the fourth plus, well, now we have some product, right? And we can just look back up here to our Pascals. It was 1, 4, 6, 4, 1. So if we write down that as 1, 4, 6, 4, 1, then we can see that we have our 1. We're going to multiply by 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. And that would be our expansion. If you also notice another little trick about this, notice that always the exponents are always going to combine to the one that you're raising the binomial to.